Alpha halogenation is a way that we can use enols and enolates and react them with halogens, either in the presence of base or acid. And the net result would be to place one or more halogens on the alpha position, alpha to the carbonyl. The base catalyzed version mechanistically goes something like hydroxide or another suitable base could abstract an alpha hydrogen, forming an enolate. The enolate can then attack a halogen such as chlorine, and again the attack is from the alpha carbon, and mechanistically we can show it assisted by reforming the carbonyl, and this also generates a Cl- species. The problem with base catalyzed halogenation is the initial product, in this case the monochlorinated version, is more reactive than the original propiophenone, and thus we often get multiple halogenations. A way to overcome this is, instead of using base to catalyze the reaction, to use acid. Common reagent system would be acetic acid and the halogen, like bromine or chlorine. And again, I'll use propiophenone as the ketone. And now, of course, in acid, we're going to form an enol in our mechanism. And the enol is going to attack the halogen, in this case bromine. And then in our last step, we're simply going to lose a proton. And we could show it mechanistically with the byproduct HBr also formed. So that's going to provide us with our monobrominated propiophenone derivative. If we wanted to, we could add another equivalent of bromine, and we could do multiple halogenations using the conditions of acid and halogens. A special variant is the haloform reaction. In the haloform reaction, what it tests for is the presence of a methyl ketone like our previously synthesized acetophenone. In the presence of base and excess iodine, you get multiple halogenations resulting in the triiodo species. And then, since we're doing this as a base promoted reaction, the hydroxide can then attack the carbonyl reforming the carbonyl causes elimination of Ci3 species, and that is quickly going to pick up a proton resulting in this benzoate derivative and haloform. In this case, iodoform, which is a yellow solid and precipitates. This is historically was used as an identification tool for specifically proving that something was a methyl ketone. Our modern ways would be to use spectroscopy. Interesting mechanism none the least. And rounding out our other halogenation reactions, included in this topic would be the Hell-Vollard-Zielinski reaction, which takes carboxylic acids that have an alpha carbon with at least one H, and using a system like phosphorus tribromide and bromine, putting a bromine alpha to the carboxylic acid. The mechanism involves first converting the carboxylic acid to the acyl bromide, and then the acyl bromide being alpha brominated and the carboxylic bromide falling apart back to the acid. Interestingly, this is the original method for how we could synthesize alpha amino acids, also just known as amino acids. So if we take the alpha bromo carboxylic acid with an excess of ammonia, we can end up displacing the bromine as HBr and making a whole sequence of amino acids based on what the R group is. We won't be responsible for the mechanism of this reaction, which is called the Hell-Vollard-Zielinski reaction, or HVZ for short. And that concludes alpha halogenation, which again, the overall goal is to put a halogen on a carbon alpha to a carbonyl. And of course, these halogens, as we've already seen, are used for a lot of synthetic reactions. This will be involved when we finally get back to our lab and we do our Wellbutrin synthesis.